Hi everyone, my name is Jorid, co-founder of Late Protocol. I'm going to talk about the new type of Merkle trees that we built for our new version of ZK compression v2 that we announced today. First, I will give a quick overview over the state compression and ZK, walk through the state-of-the-art of Merkle trees on Solana, go deep into batched Merkle trees, and then compare current Merkle trees to batch Merkle trees, and wrap up with how batch Merkle trees improve ZK compression. So what do you want to achieve with state compression? So we want to scale Solana state beyond the Solana account model with cheaper state for every long-tail application without sacrificing concurrency and parallelization. How can we achieve that with Merkle trees and ZK? What you essentially do is you trade compute units and instruction data for rent. So you don't need to pay rent anymore, but your transaction gets a bit heavier. What you essentially do is you commit state to a Merkle tree. Then when you want to mutate it, you prove that it exists. You nullify the old state. You create the new state. We use ZK proofs for their constant, in particular, growth 16 proofs for their constant proof size. For example, you can see like a Merkle tree can fill up instruction data quite quickly. But if you wrap a Merkle proof into a ZK proof, then you profit from the constant proof size. One Merkle proof in a ZK proof is 128 bytes. 8 Merkle proofs are still 128 bytes. So you can use it quite nicely to optimize your instruction data. The state-of-the-art of Merkle trees on Solana is variations of sparse Merkle trees. Sparse Merkle tree, as you can see, is quite memory efficient. So you just need to store the roots and the subtrees in an account. This works well for appends, so you don't need to send any additional data. You can just append. Updates are a bit more complicated. You don't have enough information to do an update. And also in a naive implementation, updates are not concurrent. So what you do for an update is you send the Merkle proof to the chain, and then you compute your new root based on this proof. The concurrent Merkle tree built for CNFTs solves the concurrency issue by introducing an extra step, which is the change log. You store some additional data on chain. You patch your proof in your transaction, and this way you make it concurrent. You still have this overhead of sending the Merkle proofs in your instruction data. You can mitigate against that using a canopy. So you store some more chain, like some more nodes on chain in your account, make your Merkle proof shorter, but your transactions will still fill up very quickly, in particular if you use more like Merkle proofs. You can mitigate against these Merkle proof sending by using ZK, as we established before with their constant size. But still, using ZK, you end up with the issue. The ZK proof doesn't give you the information you need to actually update the state root of the Merkle tree. So how you can work around that is by using a queue. So you insert the value that you want to update into this queue, and the third-party actor will send the Merkle proof on your behalf and have this overhead. But you as a user, you don't care. Your transaction is small and concise. This is how ZK compression v1, which is currently deployed, works. The drawback of all these sparse Merkle tree variations is you do have you have a lot of hashing on chain, which is expensive. In particular, if you want to use ZK proofs, you want to use the Poseidon hash, and hashing. One Poseidon hash costs 800 CU, so for a height of 26, it's 24K CU. The idea behind batch Merkle trees is very simple. You want to batch all of these hashing, everything you can, into ZK proofs. So not only the inclusion proof, which we already do, which wraps the Merkle proof, but now we also want to wrap the Merkle tree update into a ZK proof, and this way get really big gains by batching all of these Merkle proofs into a single ZK proof, which we can execute in a single transaction. To implement batch Merkle trees, you end up with an architecture like this. You have two accounts, which are both queue accounts, and you group the remaining Merkle tree data with the update queue. The reason to group these two data structures together is because if you want to update a value, you want to prove that it exists first. Then you end up with two actors in the system. Like in purple, you can see the user. The user doesn't really interact with the Merkle tree itself anymore. The user just inserts values into these queues. And then we have a node server which performs the actual Merkle root updates and computes the heavier ZK proofs. In the following slides, I will walk through these insertion and update operations one by one. Well, let's start with the append queue. So the setting is, with our user, we want to append a value to the Merkle tree. What the transaction does is it actually does a queue insertion into the append queue. The first step here is to add the value you want to append to a hash chain. And this, we add the value to this hash chain so that we have a concise input for our ZKP, with which we want to update the Merkle proof later, the Merkle tree later. We use, in this case, 600 of these hash chains. Every hash chain itself is like a batch that from the other actor is inserted into the Merkle tree later. We use these distinct batches because for proof verification, you need constant values on chain. So if we just had one hash chain and somebody would do a transaction, the proof for the Merkle tree update is going to fail. The second property that you want here is instant accessibility. In comparison to using a concurrent Merkle tree where you generate a root by hashing things on chain in the user transaction, here you just insert values into the queue, so you cannot use a Merkle proof or the ZK proof of a Merkle proof to prove inclusion of your state immediately. And instead what you do is we store the values in plain text in the queue account. We just look them up by index, do a comparison, and we're done, which is also quite CU efficient. The second user operation is the update operation. Works quite similarly. You have the setting user inserts value into the queue, to the update queue. First step here is you want to prove inclusion of the value that you're modifying, either proved by index or by ZKP if your value is already in a root, not in a queue anymore. Second step is added to the hash chain. Same purpose as before. We want to create these batches that we can insert with ZKPs into the roots later. Then there's one more property that we need for security. So we need to make sure that every update that is queued is unique, and we don't have two updates for the same leaf queued. We achieve that by using a Bloom filter. We use them because they're very memory efficient. Bloom filters have the difficulty, though, that it's hard to delete values from a Bloom filter. So for this reason, we use two, and we just fill up the first one. Once we filled up the second one to a certain extent, we just wipe the first one completely. So we don't delete individual values, we just delete the whole one, and this way we can keep rotating through these Bloom filters through our batches. Moving on to our node operations. So we have two node operations, one to insert the values that we have accumulated in each queue. Let's start with the appending from the queue account. So the setting is we have a node. This node listens to the append queue account, waits until it sees that a hash chain has filled up. Then it computes a ZK proof off chain. Once we have computed our ZK proof, we send the ZK proof with a new root to our Merkle tree program. And on chain, we get the old root from our roots array. We get a next index from our tree metadata. We get hash chain from our queue account. We verify the proof, and we insert the new root into this root array. The second update operation from the output queue works pretty much in the same way. The main difference here is that we We don't have the next index operation, so the setting is exactly the same. Node listens to the queue. Once the hash chain has filled up, starts to compute this proof, once the proof is done, sends the instruction data, proof a new root, verifies the proof on chain, and we're done. We have our new root. In comparison to the concurrent Merkle tree, the batched Merkle tree gets us a 20x improvement for append operations and a 14x improvement for update operations. And very interesting to note is that our batched operations are completely independent from tree height. So we can use height 23, height 30, height 100. It doesn't matter for on-chain operations. Of course, for your proof or off-chain, it does matter. Verification time is linear, but is constant, but proving time is linear. So you don't want to use a height 100 tree. These gains translate quite nicely into ZK compression v2. So in ZK compression v2, we use tree height of height 32, up from 26 before. For account creation, we get a 1.6x improvement. For account update, we get 3.5x if you prove by index, 1.3x if you prove by ZKP. And then the biggest gains that we were actually after is the Merkle tree update operation, which gets us a 250x improvement. And the nice property here is that because the instruction data for this operation is pretty small, it's less than 200 bytes, we can actually put up to 5 of them into one transaction. So for transaction cost, you can get even bigger gains than the 250x. ZK compression v2 is currently in audit. Will launch in Q2 this year. It's open source. Check it out. Thank you for your attention.